Okay, let's try to continue to the next video sections. In this opportunity, we will discuss this topic, superpoints, and there are some work. And in this particular opportunity, we will select this paper from ICCV 2021. And this paper, this tries to address this third issue that we listed before in the previous video sections. And let's try to discuss more details, and starting with the motivations of this work. As we discussed before in the previous video sections, semantic segmentations on the large-scale points, for example, like millions of points, we have some issue. It is computationally expensive, and so that the common approach, they usually need to split into smaller size. For example, if we have, again, this million of points, we will split, for example, into 1 by 1 by 1 millimeter cubic. And we will infer, for example, this one, this first split and the second split. And then we will infer for every split into the network independently. And this kind of approach will have some drawbacks. The first is we lose the global relationship because, again, we infer every individual splitted data here. For example, if we infer this particular area here, if we take the wall input here, we have the context of this surrounding, right? Like, oh, this is the next of this is chair, so this is should be also chair. We have this kind of global relationship if we take this wall as the input of this network. But since we have, again, we split this, we lose this global relationship. And then we also find this possible non-smooth predictions on the transitions, again, because we infer this independently. Probably in this kind of transitions, the segmentations are not very smooth. And this work tried to address this issue by reorganizing the input into a simpler representations. That is, they try to formulate the large scale of point clouds as the compositions of superpoints. What is superpoints? Superpoints, we can think that it is for every superpoint, it is a cluster of points, where in the same cluster, they have same semantic, like homogeneous semantic. Let's see some illustration here. So for example, we have this indoor scene point cloud like this, with the corresponding semantic we can see with the different colors here. And then the lower figure here is the corresponding superpoints. Here, for every superpoints are drawn in the same color, like this superpoint, this is another superpoint, this one, and so on and so forth. And then we can see that every superpoint, they have the same semantic, like this belongs to the projector screen here, and this superpoint belongs to the semantic of wall, and this belongs to the semantic of table, and so on and so forth. And usually when we decompose a set of point cloud here, into superpoints, we expect two properties. The first is this one. For every superpoint, we need to be, all the points are to be homogeneous in the same semantic. And the second, we want to have as few as possible of the number of superpoints. For example, if we have 1 million here, we want to have a few of superpoints. In this case is, for example, like 1000. If we can have lesser than this number, it will be better. But yeah, you got the idea. These two properties, the homogeneous and also less number of the superpoints. And then finally, if we get these superpoints, instead of classifying every point here, when we do the semantic segmentations, we will classify every superpoints here. So the unit become superpoint. Again, instead of we classify like 1 million point, we will classify around 1K superpoints. And to get this every superpoint, we can use like a common approach. For example, we take this all point features belong to the same superpoint and take some aggregations, for example, like average pooling to get the one dimension, like the single vector, one vector, and then this is the corresponding emitting dimensions, and then we will map these vector features into the corresponding label, semantic label, that can be voted by all the semantic label here correspond to these superpoints. Yeah, so this is the motivations of this work on tackling the task of semantic segmentation on the large scale point clouds. And let's discuss about the high level idea, how this particular work, this paper, tackle this problem. And I want to emphasize that this paper, it needs point-wise labels. There are some papers that do not really require point-wise label, but yeah, in this particular opportunity, we discuss this paper. Okay, so let's start by seeing this from the beginning. So given the number of point n here with the pi 3 is the xyz here, which is the point coordinate, we try to compute the point features by using, in this case, they use point net. And we already discussed how we can extract the point features by using point net in the early video sections. You can check in this playlist. So we get this number of c here, c embedding dimension, and this is the n points. And then this is the original point itself, point coordinate, and we concatenate so that we have the number of points, original 3 coordinate, and the corresponding c embedding dimensions of the point features. And then from here, we can compute the initial superpoint center. This is the initial superpoint center by using the FPS, farthest point sampling. We also already discussed in the PointNet++ video sections. If you are not familiar with this FPS, you can refer to that video. So after we sample by using this FPS, we have this M superpoint center. Let's give some numbers. For example, the number of n point here is 1 million. And then we sample, let's say 1k superpoints. And this corresponds to the center of superpoints. To get this tree, we apply this FPS. And then to get the C, the paper, instead of doing FPS directly in the C here, they consider from the original point coordinate. Let me give you some illustrations. For example, if we have this kind of point, and then let's say we have the superpoints center here and here. And then to get the C in this, oh my god. Let me draw again. This superpoint here and this superpoint here. To get the C here, we consider the neighbors. We consider the neighbors. And then for this neighbors here, we query the corresponding point features here, corresponding point features of C, and the paper average these point features to get this initial centroid for superpoints in the feature space. So finally, we will have 2 superpoint center. The first one is in the original XYZ coordinate, and the second one is in the feature space. Okay, so this is the superpoint center. And finally, we will do this block. It will estimate the relationship, the association map. We will discuss later. Okay. Ideally, we want to capture n by m, right? N is the number of points, m is the number of superpoints. So we want to capture this. We can think this is attention metric. We have this kind of metric. Later, we will assign for every n into which superpoint by seeing this row, which superpoint having the highest attention value. This is the ideal one. However, if we capture this whole relationship, it is expensive. We can think that this is 1 million and this is 1K. And capturing this large matrix will be computationally expensive, right? So this paper, instead of doing that, they only consider, for every n points, they only consider the nearest k superpoints. So instead of this, capturing this, we will capture this association map. This is n, number of points, and this is the k, which is the k nearest superpoints from every point. This is what we want to capture in the final of this pipeline, network pipeline. Okay, so after we get this initial association map, we will use this to update new center. So this correspond to this. Okay, so this is the center superpoints in the XYZ coordinate, and this is the center in the feature space. Again, we will use this association map here to compute the new center. And then using this new center, we will compute again this association map and we iterate this again, and again until we settle, we convert into a good superpoints decomposition. Yeah, so this is the overall pipeline. And then here, this method, they consider both coordinate space and also feature space. Here, coordinate space and also feature space. And this is the corresponding input coordinate, and also this is the feature space. Why we consider this? This is obvious if we consider this XYZ, because usually a superpoints will be close together in the original geometrical coordinate here, right, XYZ. But sometimes we also have, like this case, for example, we have chair here, we have another chair here, and this is like a room, indoor room. So probably this chair and the second chair, geometrically, probably they are not very close in the original coordinate XYZ, but we expect that because they are belongs to the same semantic, in the feature space, these two are close together, right? So that's why we also consider both features and also coordinate space to build this association map here. Okay, so that's it, the high level idea, and we will discuss the more detail about how we compute this association map in the next few slides. Okay, so this is the module that we have previously here. Let's discuss the detail. Previously, we have the superpoint center. This is in the coordinate space, XYZ, and this is in the feature space with the M superpoints. And this is the point features. This is the original point XYZ with the number of point is N. And this is the number of superpoint center is M. And again, we only consider the K nearest superpoint for every point here. So to do that, we query the nearest superpoint center for every number point here. And after we get that, we subtract this to this here. And then we will have this result, right? The n by 3 is basically this one. And because we subtract to the number of k nearest neighbor, so we have the additional k dimension here. Likewise, this output, we subtract this to the nearest neighbors of this feature space here, and we subtract k times, so we have this k here, additional dimension. And then after we get this, in this layer, basically we just map into another embedding dimensions by using MLP here. We map into the same consistent embedding dimension, in this case is C. C here, this is C, this is C, this is C. So here from 3 to C, and this one original is C, we again map to another C, and likewise also this 3 to C, and then this is C to also C here. And finally, after we get this, we try to proceed with these operations, these matrix multiplications. And after we get these two, we will merge by using these element-wise multiplications, and finally we will get this. Okay, we will discuss these details operations right now. So let's see this one. We will compute the association map here. To get this, first we will compute the association map in the coordinate space. See the orange lines here, this and also this. Okay, in the orange lines here we have the original point cloud here. Original point cloud and map by using MLP into embedding dimension C. And to make the explanation simpler, to understand it better, I draw here only one. One is for every single point here. So this is n point. I just draw 1 point. And then the corresponding superpoint center features is here. I also take one of the n here. So the dimension is C and K. This is C and K. And to get this, we multiply. Metric multiplications, right? It will have like this, 1 by K, 1 by K. And then we repeat because we have n number of points. We repeat again, and finally we will have the here number of points by K. We get this association map here, N and K. But we get this association map by only considering this original in the coordinate XYZ space, not in the feature space. Next, we will also do the same, but using the purple lines here, which consider the feature space. We also do the same like this, and the result we also have this metric n by k. So we have n by k here. We have n by k here. This is also n by k. And finally, this paper, they merge these two together by element-wise metric multiplication, and they do softmax normalization. And finally, we have this association map here. Okay, so after we have this association map, again, we can use this to update the new superpoint center here. We use this to update this new superpoint center. How we can do this? Again, we also do in the both coordinate space and also the feature space. Let's see the illustrations in the coordinate space here. So in the association map here, we have n by k. And in this case, we want to have the m by n here. N is correspond to this one, and k is correspond to m here. But in this case, is the k is subset of m, right? For example, like in the first point here, let's say the k nearest superpoints associated with the first point here is the second superpoint, the sixth superpoint, the eighth superpoint, and so on and so forth. So in this case, the two superpoint, the second superpoint, we will assign here, right? This value attention here, we will assign to this. And also this sixth of this superpoint will assign to this. And so on and so forth. We will need to like record this mapping from subset of k into the total m superpoint here. For example, we can build these associations using the map or like dictionary. Okay. And then the remaining points that are not associated in this k, we will have 0, right? So that's why this association map, the large association map, which is m by n, is a sparse metric, not like this one. This is n by k. This is not sparse. So after we have this association map that is sparse, we will multiply this to the original point, this one, original point, to get the new center. We can think that basically this is similar to k-means clustering, right? But instead here we use the neural network to learn the cluster center. And we will use this soft membership that are captured in this association map here. So we can think that this is a weighting value like soft membership to every point here. And finally, we will have the new superpoint center here, like this, and so on and so forth. Okay, so that's it for computing the new superpoints in the coordinate space. We can also do the same in the feature space, similar to this, but instead of 3 here, we have the number of C here. So it will be C, it will be C. Finally, we will have the new M superpoint center in the feature space. Okay, and after this, we can repeat again by computing this feature output here and map into this another features dimensions, and again compute this, and this here, and so on and so forth until we converts into a nice superpoints cluster. Okay, so that's it. And yeah, again here to assign every point into which superpoints, we can just see this association map here. For every point, we can see this direction, which superpoints having the highest attention value. That is the detail how we can derive this association map. And let's see how we can encourage a good association map by utilizing the two losses that they employ. The first loss function, they use a consistency loss here. And this is the illustrations. Here we have the superpoint cluster. We draw two superpoint cluster here. First, we want to derive a superpoints label here. Superpoint label here by weighting all the members point in the every superpoints weighting here. How we can do this weighting? It's simple because we already have this association map. We can use this. This is the number of superpoint. This is the number of points, and we multiply to this number of n, and this is the original class label in the one hot representation. For example, if we have the first point belong to the first class, we will have the 1 and the remaining are 0, 0, 0, and so on and so forth. We multiply this metric multiplications, and the result will be m by s here. S is again the number of semantic class label. So finally we will have m here. We draw only m is 2, so this is also only 2. And then in the another directions, we want to reconstruct back from this superpoints level label into every point-wise label here by using also weighting value by using this association map here. In this case, we transpose here m by n, this is n by m, and we multiply by using here. This is correspond to this here. We use this to reconstruct back to the original number of points, and the result will be n by s. N is the number of point, and s is the number of semantic label. And then finally, we can encourage the consistency in these both directions. Here, these directions, and also these directions. In this case, we enforce the consistency in the superpoints level. And then in the another directions, we enforce the consistency in the point level here by minimizing these two here. We have this, and we also have this. This will be also m by s, and we want to encourage these two should be the same. These two should be the same. This is n by s, and we also have this is n by s here. Oh, to get this one, we do this by voting. Like here, we vote this cluster, and this belongs to the red semantic, and this cluster belongs to the green semantic. So by minimizing these two loss functions, we want to encourage that for every cluster here, it should be homogeneous, should be consist of the same semantic label. By what? By learning this a good association map. Because when we compute this, right, we use this association map as the weighting value to the original class label here. Okay, so to give more intuitions, because here we have this cluster here, we have a green point here. So the red in this superpoint label here, this is not really red because we have some kind of dirty data here, the green one here. So make this not really red. And also here, because we have this kind of wrong assignment, this is also not really green, the label. So if we force this consistency to here, we want to force this to be the same as this, right? So to do this, the network will assign more attention this to this cluster. And also it will give this high attention into this cluster. So finally, after several iterations, we will have this kind of homogeneous cluster by minimizing both this in the superpoint level, also this in the point level. In my opinion, this is the main loss that trigger this homogeneous superpoints. And then the additional loss, they also employ this compactness. I think this is a very obvious. So this loss try to encourage that the superpoints to be spatially compact. It means that the point belongs to the same superpoint. They should be close to the superpoint center. So this is the point. This is the superpoint center. We need to minimize this distance. And to get this superpoint center, it's easy. We can just compute this using association map here, multiplied by the number of points by 3 here, x, y, z, and finally we get the center here. That's it. We just minimize this. And this is the experimental result. This paper tried to compare with the previous state of the art, and we can see that their work, they achieve a lower number of super points, which is what we want, right? This is a substantially higher number than this one, and this is also still have a larger number super point than this one, right here. And if we can see here the qualitatively, for every super point here, they also belongs to the same semantic here. It means that the homogeneous property can also be achieved by using this method. Here also belongs to the same semantic. Here belongs to the same semantic over here. Okay, so this is the superpoint result. And then this paper tried to demonstrate these superpoints to be used in the semantic segmentation here. Again, to get the semantic segmentation, if we already have these superpoints, one of the common method will be we aggregate these features in every superpoint here into a single vector. Single vectors like this, 1 by e embedding dimension, and then we will map this into single semantic value. And we can, for example, voting the corresponding label here, like this will vote this label. It will be the screen projector label to fit this. So this will be fit into this semantic screen projector. That's how we can do the semantic segmentations in the superpoint based method here. And in the upper numbers here, they use the original point based semantic segmentation. So again, if we have like 1 million, they will split into smaller set, and then they will predict every point. And in the super points, again, we will predict for every super points instead of point. It will be, for example, like 1K, which is much lower than 1 million. As we can see here that this paper, SPNet here, they achieve the highest performance in terms of IOU accuracy and overall accuracy. Yeah, so I think that's it for this work, and see you in the next video.